Today we are going to be looking at bivariate data and key features of a graph that we get when we're looking at those scatter plots and best fit lines that we talked about yesterday. So we're going to pull from the data we had yesterday instead of starting from square one. So yesterday we talked about info with how much water you drink and how many miles you can then run, right? So if we flip back to that, okay, that was on page 27. The equation that we got as the best fit line was y equals 0.3x plus 0.6. Okay, so we got y equals 0.3x plus 0.6. And if I want to draw that line on here, you might go, oh, I don't want to start at 0.6 and count up 0.3 over 1. We don't need to do that. Again, we can just do what we did yesterday and find the 2 points that it came from. So that 8, 3 and the 13, 4.5. Use this number here, right? And this was our best fit line, right? We wrote the equation of this line that went through these points. Okay, that's not a perfect line, but close. Then we want to be able to talk about what do all of these things mean? What does this information tell us? So all those other key pieces we've been looking at, what is the slope? What is the X-intercept? What is the Y-intercept? Those still come into play, but now we're doing it with data information that we created, right? We wrote the equation of the line. So what is that information telling us? Well, we know that our slope is 0.3. The reason why we know that is right when we look at our equation, it's sitting in front of the X. Well, what does that represent in this situation? We know that slope is always a y per an x. So we know our y label is the distance that they run per cups of water. So we know that for every 0.3 miles, right? 0.3 miles is going to get a cup of water. So if you drink a cup of water, you'll be able to run 0.3 miles further. Now, we might say, is that really true? Well, this is just the data that we got off of this. There's probably other things that come into play. We'll be talking about that as we continue in the unit as well. Okay, what does the Y-intercept represent? Well, we've talked about the concept and idea that our Y-intercept is always a starting point. Again, it is still a starting point, but what does that starting point mean in this particular situation? Keeping in mind that a Y-intercept always means that our X value equals 0. So we know our Y-intercept here is 0.6 because that was our B value. And we know that this has something to do with our starting point and something to do with our X value equaling 0. So our cups of water equaling 0. So this is telling you how much you can run if you don't drink any water at all. Now, if you don't drink anything, right, you'll be dead. Morbid, but true, right? So, but what about people who only drink soda or only drink fruit drinks or only drink other things? Right? That's maybe a piece that we would consider in here. But it's saying if you don't drink any water, you at least have a base value that you can run 0.6 miles. Now, does this graph have an X-intercept? No, that's where a graph would cross the X-axis. So this doesn't have one. Well, why don't we have one? Well, it should be reasonable to us that when we're dealing with positive slope, right, data that's going uphill, we're never going to come back down to that X-axis, right? We have positive slope. Now, there is an X-intercept somewhere, right? But that X-intercept is happening way over here in an area that doesn't make sense. It's not reasonable, which is then going to lead us to our next question. Would this be a line that continues forever? Normally when we graph a line, right, we'd extend across and we would place arrows on this. Do we really truly need arrows on this line? Well, if we did, that would be saying if we drink negative cups of water in a day, we can run 0.2 miles. Well, we can't drink negative cups of water, right? That doesn't make sense. I guess if you're ill. Okay. We can't consider, okay, yeah, what happens if we drink 16 cups of water? That's fine. But if we keep going, it's going to make sense to say, what happens if we drink 50 cups of water, 100 cups of water? Well, that doesn't make sense because then we're going outside of our reasonable domain, right? This doesn't go on forever. This line does not continue forever because we would leave our reasonable domain. We leave what's reasonable. And when we're talking about real life data, we need to make sure that we're in a world that's actually reasonable and something that makes sense. Okay, so if we put all of the information then together today, stuff that we did yesterday and that piece we just added, let's look at this situation. So the following data shows the temperature at different levels of elevation, so how high you are, that's elevation, on Mount Fuji. Okay, so we know one of the first things we want to do is make a scatter plot. Well, we've got some really big numbers over here. So are we going to want to count from 0 all the way up to 2250? No, right? So we said, what if we talk about this being in thousands? So if we talk about this being in thousands, we can change these numbers to 1, 1.25, 1.5, 1.75, 2, and 2.25. Now, the good news is that this is in meters. So if we say elevation in meters, but we want to turn that into thousands, if you really remember those labels in science, right? Like meter, deca, hecta, kilometer, right? Thousands is really kilometers. So we really would just be switching this from meters to kilometers. I'm not going to assess you on that piece. So if you say, ooh, I don't really know what that is, and you would say elevation down here, but you would do this as meters and thousands, I'm not going to take off points. Now, I do think it's also reasonable to just say that it's kilometers and know that we're making that switch. So if we need this label in here, we just need from 1 to 2.25. So, I mean, if we count just by even 0.25s, right? So 0, 0.25, 0.5, 0.75, 1, 1.25, 1.5, 1.75, 2, 2.25, 2.5, 2.75, 3, right? That gives us enough distance there. And then for our temperature, right, we do need to make sure we're always starting at 0. So maybe if we're counting by 10, something like we've done like that on the way on the other side up. So this is going to be our temp. Didn't leave as much room and space on this one, sorry. So let's see if I do 5, 10, 15, 20, 25, 30, 35, 40, 45, 60, 70. Okay. So we know when we are at 1,000 meters or at 1, this is going to go with 71. So yes, we're going to have to approximate a little bit, but that's the best we can do. When we are at 1.25, we are at 68. Oh, it's gone down a little bit. When we are at 1.5, we are at 63. Right? The higher we go, it looks like the colder we are getting, which should make sense. Now we're going to be at 57. 2,000, we are at 54. 2.25, we are at 50. And by golly, this looks like a really darn stinking straight line. So if we are picking 2 good points here, we can't go that wrong. The first 2 points might be a little bit off, but everything else is pretty darn stinking close to a good line here. So maybe if we decide to pick this, let's see, I want to pick points where I can avoid the weird decimals. So what if I start with my first point and my second to last point, because this is now 1,71 and 2,54. And those numbers, then I don't have the 1.75 or 1.25 in there. So if I want to write my equation of my best fit line, okay, so now if I'm going into my best fit line here, I'm going to pick those 2 points. So first thing I need to do is find the slope. Now, we should be getting a negative slope, right? Because we should agree this trend in data is going downhill. So this is telling me that my slope is negative 17. Now I'm going to pick a point to go with that, and I'm going to plug this into point slope form. So y minus 71 equals negative 17 times x minus 1. I'm going to solve that for y. And I'll get y equals negative 17x plus 88. So I'm saying that's my best representation, right? Here's the line I'm going to draw in here. I mean, this is a really stinking close to going through all of these points. Okay, so what does our slope represent on this one? So our slope here we got was negative 17. Okay, we always know it's y per x. It's the temp per kilometer. So this is telling us that the temperature is decreasing 17 degrees every kilometer. Right? If we raise an elevation a kilometer, our temperature is going to drop 17 degrees. What is our y-intercept? So we know our y-intercept from this data is that it's 88. Well, if that's our starting point, okay, what is this problem talking about? It's talking about temperature. It's our starting temperature when we're at ground level. Right? It's our starting temp before we start to go up and climb Mount Fuji. Does this line continue for forever? I think we should again agree that no, it doesn't, because it's not reasonable. I mean, we can't go to an elevation at a certain point. There's not going to be anything that high. We can't go to an elevation and end up at a temperature where we're frostbitten, right? There's certain points that we just can't consider. Now, this graph does have an x-intercept. So this is something that we could consider. Okay, the x-intercept, remember, we do not just easily see. The x-intercept we find by plugging in y equals 0. So if I say 0 equals negative 17x plus 88, this is an equation I can solve. I'll divide by negative 17. Now I'm going to get a decimal. So this is about, I'm rounding to the nearest tenth. This is about 5.2, right? We get 5.176, right? It's about 5.2. So this x-intercept is at 5.2. Over here, right, on our graph, over here would be 5.2. What does that mean? Well, ending point is a little bit different when we're talking about elevation and we're talking about temperature. Can we have negative temperatures? Yes. So could this graph still continue past this point? Yes. Now, is it going to continue forever? No. Right? There's certain temperatures that aren't reasonable for where we could actually go and all of those types of things. So what's more important is it's telling us when our y value is 0, when our temperature is 0. We are saying that when we are at 5.2 kilometers, our temp would be 0.